Hello everyone, welcome to the 10th lecture of the course Advanced Structural Analysis. This is the last lecture on the week 2 and we will try to discuss the effects of the temperature loading and the member pre-strain on the given system. At the same time, we will also try to see the post-processing of the given system. As a concept which will be covered through this session, we include the general temperature change, the inclusion of the support, yielding and the member pre-strains in the system, and also looking at the post computations in the simple flexibility approach. As our intention in the previous session was also there, that we try to include the secondary effects of the given loading, which typically conclude the effects due to the temperature, due to the member pre-strains, due to the support yieldings in the given problem. We considered one way to accommodate them by considering them in the direction of the redundants which have been selected, so that these conditions become the necessary compatibility conditions of the given system. But in multiple cases, it is not always possible to define these effects in the direction of the compatibility conditions or in the direction of the redundants, and in those situations we need to accommodate those effects as the parameter of the external load in the given system. Now, as we start with the given system, we consider over here the amount of the delta L which is contributed is now the net amount of the load distributed due to the direct load, due to the temperature, due to the member strains, as well as the support yielding of the given system. And these are the conditions which are defined when we do not have the provisions to select these parameters of the deformations in the directions of the redundants of the given system. Typically, these all effects are considered as the secondary effects, and we have already seen that statically indeterminate systems have considerations where these effects can introduce the internal stresses as well as the internal resistance in the given members, and that need to be accounted, which is not similar to the statically determinate systems. Now, in order to define these individual terms, we consider that the overall displacement in the direction of the redundants which has been calculated will now be adding the contribution of these components with respect to the temperature, member pre-strains or the support yielding in the given system as well. Now, as a first case, we start with the inclusion of the temperature loads on the given system. We have a given system where we consider a simple beam which is a fixed ended beam on both the ends, and the system is subjected to some temperature gradient which is at the bottom of the system T1 and reaching at the top of the system T2 of the given problem. Now, one can consider this as simple criteria where the cross section of the system is defined, and on the cross section at the bottom we have a temperature of T1 and at the top the temperature reaches to T2 value in the given system. In between, the gradient of the given temperature is defined to vary linearly for the given problem. Now, what we can understand from this, as the system is subjected to a temperature gradient between the top and the bottom flanges, the system will undergo some amount of bending, as the bottom fibers will experience the more amount of stretching or more amount of tension, whereas the top fibers will be subjected to the less deformations and they will be subjected to the positions such that the overall deformation considers that one end of the given system is under compression and one end of the system is under tension of the given system. And under the application of these kind of primary behaviors, the system will experience a similar condition which is identically defined in the standard bending theory. So, what we do here in order to accommodate the effect of these temperature loads, we consider that through the beam thickness of the given system, the reference surface is identified. It is the reference fiber at which the no change in the length of the member takes place, and we consider this system at somewhere in the middle of the given problem, as it is considered to be undergoing bending. With respect to the reference fiber of the given system, we consider the temperature profile, and this temperature comes out as T1 plus T2 by 2. Now, it appears that with respect to this reference temperature, the given temperature on the top and the bottom changes, and that leads to the bending deformations in the given system. In order to identify these deformations, we simply consider a simple idea of the strain taking place on the given problem. This value of the strain measure can be evaluated by the simple representation that strain in the direction of any one of the compression or the tension side can be represented as alpha into delta t, and this is the measure of the strain which is represented with respect to the delta t value being defined with respect to either T2 minus the t as the average value of the given system, or if we go at the bottom of the given system, this could be defined as alpha delta t, and this delta t value can be defined as T1 minus T average for the given system. And accordingly, one can describe that for the given problem, these values according to the classification will typically appear as T1 minus T2 for the given cases, T1 minus T2 by 2, which typically means that I can identify the delta t as a general expression of T1 minus T2 by 2 for the given problem. Now, at the same time, we can consider that the amount of the stress which is described for the bending problem is reflected by the standard expression m upon I into y, where m happens to be the bending moment in the given system, I is the second moment of area, and y is the distance with respect to the reference axis or the axis about which the strain values are 0. Now, we consider this problem in the similar manner, and we consider that the sigma value is equivalent to the elastic modulus and the strain in the given problem. And as we identify using this expression, the expression of the moment, we get to know that with respect to these far ends where the strain values have been identified, we evaluate the value of the moment as EI alpha delta t upon d by 2, and in this condition, now the delta t, if I consider with respect to the T1 minus T2 by 2 expression, I can write this expression as m of t, the moment due to the thermal profile, is equal to EI alpha T1 minus T2 upon d in the given problem. So, the half factor from both the portions, from the delta t fraction as well as the d by 2 fraction, can be cancelled out, and in this manner I can describe this as the general expression. In many of the reference texts, this expression is also written as EI alpha delta t upon d, which simply refers to the same condition, but one must understand that the delta t reference is corresponding to the ends of the given problem T1 minus T2, whereas in the actual derivation we consider it with respect to the average temperature at the middle of the given system. Now, with respect to this idea, we understand that for any given system which is subjected to the temperature field, the moment profile or the moment distribution is described in the given problem, and that moment distribution is described as the simple value of mt, and this is described by this formula. Now, in a general case, if we have a loading in the given system, we consider the redundant problems like in a simple manner, that we can consider the two set of reactions at the two ends as the redundant R1 and R2 for the given problem, and with respect to these redundants, we can have now the three systems: one statically determinate system, second system having the first value of the redundant being 1 unit, and the second or the third system having the value of the redundant 2 being 1 unit in the given problem. Now, the first system which we have considered should be considered with respect to the external load. As we do not have a direct load in this given system, we will consider that this given system is subjected to the temperature loads of the given problem. So, the criteria of the loading which we initially wanted to evaluate with respect to the displacements in the directions of the redundant can be now compensated by this given system, which will give us the temperature distribution and corresponding to it the amount of displacement in the direction of the redundant 1 and redundant 2 due to this temperature field. Now, as we have described the moment distribution due to it, we can also describe the moment distribution due to the first redundant system, we can describe the moment distribution due to the second redundant system. Now, one can calculate the standard flexibility equations which are described for the given system, and we can write it as delta 1 and delta 2 for the given problem are delta 1 due to the external load plus delta 1 due to the temperature part plus delta 1 due to any other kind of secondary effects of the given system, which we are including corresponding to the pre-strains or the support yielding or all the parameters at this point, plus f of 1 into R1 plus f of 1 into R2 in the given problem. In the same manner, I can go with the second, and I can describe this as delta 2 with respect to the load, delta 2 with respect to the temperature, delta 2 with respect to the all secondary effects of the given system into f of 2 into R1 plus f of 2 into R2 for the given problem. Now, with respect to these given loading components which are corresponding to the direct load, we can consider that as there is no direct load active on the given system, these components are 0. The components with respect to the temperature distribution can be evaluated now in the same manner as we do the simple loading calculation. Only difference will be that instead of considering the net moment due to the load distribution, now we are considering the moment distribution due to the temperature profile. So, the delta 1 T is same m1 m dx upon Ei, but the m expression is the m of T for the given problem. Similarly, delta 2 T is also the same expression, only the m expression is m of T, which is the distribution of the moment due to the thermal profile in the given system. Once we are able to accommodate these values, we can again calculate the flexibility matrix of the given system, which will be done in the same manner as we did earlier, and from these given calculations we can evaluate the standard value of the given system, which is described by this expression. The flexibility matrix has been calculated similar to as earlier. The values of the parameters of the temperature load delta 1 T and delta 2 T have been described by these expressions. We can now see that MT is equal to Ei alpha T1 minus T2 upon D. M1 expression has been identified. We can calculate these values, and this value comes out as alpha delta T L by 2 upon D, and this delta T expression is T2 minus T1 minus T2, which is the larger temperature minus the smaller temperature. In the same manner, we can also evaluate the delta 2T for the given system, which is the rotation at the joint 2, and this comes out again as del alpha delta T D L upon 2, and this has been described over here. So, with these two expressions in place, we can now evaluate the values of R1 and R2, and we get the values of R1 and R2 in this manner, which means that R1 comes out with the value of minus and R2 also comes out with the negative value, which means the initial forces or the initial directions which we considered for the reactions or the redundants in the given problem, which were described in this manner, the redundant values are opposite to that, and the value of the redundant forces are equal to this value. So, once we are able to know this, we also understand that this is the standard expression for moment at the end of a fixed ended beam, which is subjected to only temperature field. Okay. So, we have tried to account for the temperature related distributions due to the given flexibility coefficients of the given system. Okay. Now, as we move to the next case, we consider a temperature strain in the pin jointed structure. As an initial problem, we have considered that the similar problem was subjected to any change of the length of a member, say the member BC, but that member BC was also the condition of the compatibility which we were defining, because the redundant was selected in the same direction, and that gave us an easier way to define the corresponding change in the length in the delta measure. But if we say that instead of having the delta change in the BC member, say we have a temperature change or increase of delta T units in one of the member BD, which is this member in the given system, and then at the same time we have one of the member AB which is having a shortening of 2 mm. So, if these two members are subjected to some kind of length change, how do we accommodate this into the analysis? As a first part of the given system, we consider that the external system is converted into a statically determinate system subjected to the external loads. At the same time, we have a redundant system 1 which is subjected to the redundant value of 1 unit. We have a redundant system 2 which is also subjected to 1 unit of the load. At the same time, we also define now with respect to the change of the temperature, we have one of the systems in which we consider the statically determinate problem, and now the first member, which is this given member BD of the given problem, is subjected to delta T length change or delta T temperature change of the given system. At the same time, we also define one more system, and with respect to this system, again statically determinate, we consider that this system is having one of the member which is AB, and this member is having shortening of 2 mm in its length. Now, considering this as a loading system, and I can consider that this is a direct load active on the given problem. This also is a loading system, but this is due to the temperature field in the given problem. This also is a loading system, but this is due to the member pre-strain in the given system. Now, I need to add the contribution of all these systems together, and we understand that the delta is equal to this given expression as per the initial discussion, and we have considered that the total discussion of the delta L can be divided into all these components, where delta DL is due to the direct load part, delta T is due to the temperature part, and delta m is due to the member pre-strain part of the given system. While the delta dl we have already seen in the previous case, where we consider the member forces in this given system as S, we consider the member forces in this given system of redundant 1 as S1, and we calculate the member forces in the given system of redundant 2 as S2, and then we calculate the value of delta 1L with respect to the given direction of the redundant 1 and the direction of the redundant 2 as delta 2L for the given problem. In the same manner, if I now go with the calculation of the delta T components or the delta M components of the given system, what we understand that corresponding to the given problem, this determinate system is subjected to a change of the temperature in one of the member. So, as we have already seen that change of the temperature, change of the length in a determinate system will lead to the change of the length of only the given member, the other members will not be influenced by it. So, I can consider that this given member will have a change of length which can be considered as the axial deformation, and that can be described as alpha delta T into length of the original member. In the same manner, this corresponding member is also having a change of the length, and this change of the length can be considered as E of x for this given member, and this is minus of 2 mm because it is the corresponding length which is being shortened for the given problem. Now, with respect to these two criteria, we understand that in the given problem, when I am trying to calculate the redundant values and their corresponding displacements for the calculation of delta 1 due to the direct load 1 in the given system, I should say the dl, I evaluated the given system as the integral, or as for the truss we do not we can directly do the summation of the given system. So, we define it as summation for the member 1 to m S1 S L upon AE for the given system. In the same manner, this given problem which has been done typically addresses that with respect to the direct loading we get in all the members some forces which we describe by S. In the second case we have S1 where the unit amount of the load is applied in the redundant direction and we calculate all the member forces, and then we do this multiplier to calculate the total energy associated with the given system. In the same manner, if I now start with the contribution due to the member pre-strain or the temperature change in the given system, I can describe it as I am looking for the displacement in the direction of the redundant 1. So, I will describe this as a virtual system, describe this as a real system for the given problem, and now corresponding to this real system and this virtual system, I will write it as the amount of the external work done is 1, which is the external load, into the amount of displacement which is taking place over here, which is the delta with respect to the point 1 and the temperature part, and this is equal to the net strain energy associated with this real and the virtual system combination, and this can be defined as the summation of I equal to 1 to m for all the members, and we define the virtual system with respect to the forces. So, S of 1 into we describe the deformations which are available in each of the members, which we call as d of Ex in the given system. If we do not want to define the d of Ex, one can directly write this expression as S L upon Ae as well, where S defines the corresponding internal forces in each of the members of the given system due to temperature. Now, in order to define this parameter, we can easily write the expression that d of Ex is nothing but the alpha delta T into L for the given problem, and this can easily calculate the value associated with the temperature change and the displacement in the direction of redundant 1. As we have only one of the members subjected to the temperature change, we will express this expression as that delta 1 with respect to the temperature is equal to S1 with respect to only the member BD, because I do not need to consider other members. All these members with respect to the loading temperature have 0 forces. So, I have this member as a say member BD of the given system into the given change in the length of the original member of the given system, and that is alpha delta T into L for the given problem. And this gives us the value of the temperature change, the value of the displacement in the direction of the redundant 1 due to the temperature change profile of the given system. I can do the similar condition for the member pre-strain part, and this could be defined as delta in the direction of the redundant 1 due to this member pre-strain and that is equal to delta 1 due to the member part, and this is equal to the amount of the force in the member 1 corresponding to the BD into the change in the length. Now, sorry, as the member pre-strain is available in the member AB, so I have to calculate the force S1 into the member AB of the given system. So, this member AB, because all the remaining members for this given system are having 0 deformations in the given system, and this S1 with respect to AB part, which is over here, into the E of x corresponding to the member pre-strain part of the given system, and this value comes out as -2 as we have defined over here. I can do this procedure similarly for the delta 2 component, which is corresponding to the redundant 2, in which this system will become my virtual system, and correspondingly 1 for the system of the temperature, and then for the system of the member pre-strain I can do this calculation. We describe this component in a very simple manner by writing it as the delta 1 due to the temperature, delta 2 due to the temperature in the direction of the redundant 1 and 2 can be described. Similarly, due to the member pre-strain, the values of the delta 1 and delta 2 can be defined, and any of these values can be described by these simple expressions. Now, as we are having only one of the force or one of the member subjected to the deformation, I can write this expression as the S of 1 with respect to the given member BD when it comes to the temperature into alpha delta T L for the given system. Similarly, when it comes to the delta 2, I am coming with this given part of the problem, and we define S of 2 for the member BD into alpha delta T into L. This is the first combination. In the similar manner, if I want to define the delta 1 M for the given system, I define it as S of 1 corresponding to the member AB of the given system, because that member AB is subjected to the member pre-strain, into the value of the member pre-strain, which is of -2. Similarly, with respect to the member BD, and that comes out as similarly with respect to the redundant 2 system, and that comes out as S of 2 with respect to the member BD AB, and this is again multiplied with the -2. And with these calculations, now I can evaluate the corresponding values of the change in the length in the direction of the redundant 1 and redundant 2 due to the loading, due to the temperature field, and due to the member pre-strain in the given system. Now, as a next case of the analysis, what we do, we consider the similar table as we have considered earlier, because we have already added these 3 systems in the given problem, but along with that we have 2 more systems in the given problem. So, what we add in the given problem, we consider that due to the member temperature part, we have the E of x or the change in length, and due to the member pre-strain also we have the E of x component in the given system. Now, when we go to all of the members out of the all systems, we understand that in the statically determinate system we have those set of deformations with respect to temperature only taking place in the member BD. So, we define the member BD over here and describe this value as E of t for the given system, and remaining all the members are having 0 deformations. When it comes to the member contributions or the member pre-strain part, we define that E of x is only available in the member AB of the given system. So, we define in the member AB the value of -2, and for all the remaining members this value is 0 for the given system. And now, as we describe the given expressions, when it comes to calculation of the given contribution with respect to the individual cases, we now multiply this E of t value with respect to S1 parameter over here and S2 parameter over here for the 2 members. Similarly, we multiply this member Ex component -2 with the member AB for S1 and S2 components to get the overall values of these deformations. So, by doing so, we can now represent this system in the simple form, where this is the representation of the temperature deformation or any kind of member pre-strain or other parameters of the given system. This is the possible deformation which is due to the support. If any of the supports have a possibility of deforming, that will be included in the external part of the given system, and this is the parameter of the given system which is due to the internal components. Due to the internal components, right now we have added in the given problem that the member BD is only having the temperature change. So, corresponding to the member BD, I can calculate that with respect to the delta 1, the temperature effect can be calculated as the amount of the member force in the S1 which is minus 1 into E of t which is for the given system. So, I can define it as minus 1 into alpha delta t into L. Similarly, for delta 2 it can be defined as the given system of the force which is minus of 1 by root 2 into E t of the given system. So, it comes out as minus 1 upon root 2 into alpha delta t L for the given system, and same has been defined over here. When it comes to the member contributions, we again go with the same part, member contribution of minus 2 with respect to S1 as it is already 0. So, we will have no contribution of the member pre-strain with respect to the deformation in the direction of redundant 1. With direction of the redundant 2, we have a multiplier of minus 1 by 2, we multiply that together and that comes out as root 2 of the given problem. So, this comes out as the standard expressions which we need to describe for the delta t and the delta m in the expressions. Once we add them all together, we get the net response of the given system. Now, as a next case, we have already discussed the basic analysis of the given system. Our intention up to here was to identify the unknown set of redundants in the problem. But if we look at the problem, the analysis of a structural system not only relies upon knowing the redundants, but we also need to know the other support reactions of the given system, the internal reactions of the given problem, and the displacements and the rotations in the given problem. So, if we need to evaluate all these systems of the given structural analysis, we need to parallelly compute all the remaining values also. Now, a standard post processing of the given system is often lengthy, because when it comes to the standard force method or a flexibility method, knowing the other responses can become lengthy for the given system, because we do not have a parallel computation of all the remaining components in the given process. Now, one possible approach which we typically can account in the given process is, as we were considering this as an original system, we considered that initially we have a system statically determinate subjected to external load, and we have considered the overall system with respect to the external support reactions also. Now, these reactions are the reactions at the ends of the given support, which are not the redundant reactions of the given system. So, now with respect to each of the value of R1 being 1 unit, R2 being 1 unit and Rn being 1 unit, at each of the point we will keep on calculating these support reactions of the system also, and as we take the summation of all these support reactions together, that gives us the total summation of the net reaction which the system will have. So, as a parallel computation, what one can do while evaluating these systems together, we not only rely upon evaluating the value of the displacement at the respective locations of the redundants to define the compatibility conditions, but while defining these free body diagrams, we also calculate these support reactions which are evaluated at each of the step, and then we can take the sum of them together to know the net reactions of these supports. In the same manner, one can also evaluate the response or the displacements of the given system. These are the displacements other than the available set of displacements which are in the direction of the redundant. As we consider this problem, at this given point we have the vertical translation which is 0, and that becomes our conditions of the compatibility. Same is with this system, the third and the subsequently all other joints of the given problem. But at the same time, each of the joint 1 to n are also defining a condition of the rotation over here. Now, what one can do to evaluate this value of the rotation parallelly in the given process, one can describe the problem into this case, which is a statically determinate system, and then at this case itself one can calculate the amount of the rotation also at this point. Of course, this is much more computationally lengthy, because earlier we were only calculating the displacement in the direction of the redundant 1, redundant 2, redundant 3 and subsequently others. Now, we are also opting to calculate the displacements in the direction of the unknown displacements or the displacement which are actually taking place in the given problem. So, knowing these displacements will of course be lengthy, but the easier way to calculate them will be that if while doing these individual calculations of the system, we can also define by the energy approach these individual amount of the displacements or rotations in the given problem, and then we add the cumulative sum of all them together to know the net displacements or the rotations of the given system. So, with this we identify that the standard force method, which is a compatibility equations based system, provides the extra equations of the compatibility and solves the indeterminate system. The release system which we define is not unique, and that becomes one of the main challenge to include these kind of approaches in the computing environment. And then finally, we understood that the simple flexibility approach is easier to evaluate the redundant forces, but the post processing or the post computation of the remaining analysis results become relatively difficult. And with this, we now look forward to look for a second method of the indeterminate system analysis, which is called as the displacement method, and we will look it from the perspective of the stiffness approach. With this, we stop over here, and we have these references which typically we followed for the week 2 sessions. Typically a number of problems are defined in both of these reference books, and as the content is very much elementary, has some part of the content from the basic course as well. So it is expected that now you can plan number of problems, try them out, so that you get the better understanding of these given concept. With this, we stop over here. Thank you everyone.